Okay.
Terrible.
It was so funny.
Welcome. We will take the area between two curves. Woo. What?
So in your search history, it's just
What?
Trying to find out.
Wait, do you have a 9th period? What is it?
how did you figure it out?
So Rose, whenever there isn't something on the board, it's always the video is always really unfocused, and it just like kills your eyes.
It needs to stick to
Also,
the
no one turns it, so you can't
we make a large, neat,
what's on
detailed
the
graph.
board.
Chico, what does secant squared look like? You might be asking. I gave you guys about 5 minutes to take care of this, so hopefully you did. And what does secant squared look like? Well, normal secant looks kind of like, between negative pi over 2 and pi over 2, it has that secant, it does that secant thing. So if you square numbers which are bigger than 1, they're just going to get like bigger. So it's going to look like, kind of the same. Okay, well, by the time we get to pi over 4, what is the value of secant squared? Well, secant pi over 4 is root 2, so then this would be 2, yeah? And it's going to be a little bit like this. So hopefully that was the picture that you had. And then, so this is the secant squared x function. And then what is the sine x function? It starts at 0. By the time we get to pi over 4, we're at like root 2 over 2, which is like 0.7. So I'm talking something like that. Agree? Okay. So the goal would be to find the area of this region, which I'm now shading. Okay, now, as Chris says, and as probably 90% of you are going to be saying duh, can I just, will Chris say it again?
take the area of the curve that is higher up and subtract from that the area of the curve.
Yes. He says, take the area under secant squared, which would be the integral from 0 to pi over 4 secant squared, and then subtract the area under sine, and that seems to work perfectly fine. Yeah? Okay, but for whatever reason, I would want to sort of discourage you from thinking of it as two separate integrals, and instead I want to encourage you to think of it as a single integral. Because, after all, integration is not just finding the area under a curve. Integration is adding up an infinite number of infinitely small things. And what I'm going to do is I'm going to partition up this region that I want to find the area of into bunches of little rectangles. And the rectangles are shaped like this. And every one of those little rectangles has one thing in common, which is, for a particular x value, the height of that rectangle is secant squared x, and or rather the top dimension is secant squared x, and the bottom dimension is sine x. So what's really going on is I'm taking the interval from 0 to pi over 4, I'm partitioning that interval up into subintervals, I'm choosing a sample point from each subinterval, so whatever, and I'm plugging it into the function and getting what I get. And what is the height of each of these little rectangles? Yeah, the height of each one of these is just secant squared x sub I star minus sine x sub I star. And then when I go to solve this problem, what I'm really doing is I'm adding up a whole bunch of things. I'm taking the so-called representative rectangle, which has height secant squared x sub I star minus sine of x sub I star. That's the height of the rectangle. What's the width of the rectangle? He says, can we just call it delta x? We sure can. And that's the ith rectangle, has that area. Now I'm gonna add them all up from I equals 1 to n, and then in order to make the approximation more accurate, I'm going to take the limit as n goes to infinity. Okay, so by the definition of integral, does this process make sense? What is this integral? Sakar, of course. It is
Secant squared x minus sine x dx.
Yeah. Sprinkle a little magic pixie dust on that. Bippity boppity boo. And we integrate from 0 to pi over 4. Okay, so dude, it's exactly what Chris said, but instead of thinking of it as two separate integrals, you think of it as a single integral measuring a single.
Instead of setting up that way, couldn't you just do the two separate
That's what I just
integrals?
said. Yep, that's what I just said. But it's better to think about it this way. More examples.
Well, no. Split them up and then put them together.
Okay,
So just mean the exact
good.
same thing.
So now just like do it. If you haven't already. If you have, you can move on to the next one. Well, this guy's ahead. So, tan derivative of secant squared is just tan, yeah? You guys like pretty much all done already? Negative signs, cosine. So that's like 1. So I got root 2 over 2. Is that what you guys got?
Yeah.
Okay, second problem, more or less the same, but different. So go. Make a picture.
Wait, so this one is just like overall.
Yup. Find the area between the two curves. You can't really begin to understand what it is you need to do until you draw a picture. So it's like step 1, draw a picture. Alright, so what's going on here? I have some line y equals negative x, looking like this. And then I have the parabola 2 minus x squared, so that's like an upside down parabola. So boom, boom. And then, well, suddenly I find myself wanting to know something really badly.
Where it intersects.
Where it intersects, so yeah, side problem. Where does this parabola equal this line? So I have to like do some math. Oh yeah, answer -1 and 2. So that means I have a point -1 and 1, and I have a point like 2, -2, which looks about right. You start to think about it. Boom. Okay, so my picture looks like that, and I think it's really, really helpful to shade the region that we are trying to find the area of. And this is kind of where my method sort of reveals itself as being a little bit superior, because now the natural way to think of myself finding the area of this region is to partition it up into a bunch of little regions, right? And so what we're really going to do is we're going to take the interval from -1 to 2, divide that interval up into subintervals, and take a particular rectangle. And every one of those particular rectangles has something in common. What does it have in common? Well, it has a height determined by has a top y coordinate determined by the parabola and a bottom y coordinate determined by the line. So I think it's really helpful to use like curly braces and to say, okay, there's my representative rectangle. Its width is delta x, and its height is the difference in the y coordinates of those two functions at those 2 points. If you try to do it as integral minus integral, you might kind of like confuse yourself, right? because like the parabola is sometimes positive and sometimes negative, and the line is sometimes positive and sometimes negative. But if you just, that's kind of weird, right? But if you just think of it as the height of this representative rectangle is simply the difference in the y coordinates of the two functions. You with me, Sushant? Yeah, then it just all totally makes sense. So this is for an arbitrarily chosen x of I star. This is just going to be 2 minus x of I star is that coordinate minus negative x of I star. And I'll probably just do this one last time, and then from now on I'll just go straight to the integral. But what I'm really doing is I'm taking that y coordinate minus that y coordinate. That's the height of the representative rectangle, and multiplied by the width of the representative rectangle. I add them up from I equals 1 to n, and I take the limit as n goes through infinity. This is, by the definition of integral, just the
Wait,
integral.
isn't that x of I star squared?
We're just gonna let him just
What?
add it in a picture too.
I am a speaker. Good. Alright, so integral from -1 to 2 of 2 minus x squared plus x. And now you just do it. You guys like done already?
Yeah.
Okay, just move on to the next problem.
Differentiation and differentiate. Differentiate.
Variable you want to use.
Oh,
Wish I was smart.
I really hope I didn't do that on a test, because there's like a high probability that I did. Yeah.
No, anti-differentiation. Anti-differentiation.
Yeah.
So did you guys get 4.5
Yeah.
for that problem?
That was also, wasn't that in,
Whoa.
well,
I think so. That mess up? Yeah, I said 4.5, not half.
Yeah, that's right.
Oh, yeah.
That was nice.
Don't copy on the board, do it yourself. Alright. I'm gonna give everyone a second to catch up, but most of you seem to be like ahead of me. Wait, don't copy up the board, do it yourself.
did I do that right? I just got the wrong number.
Oh, it's after 2 minus after 1.
You gotta be really neat and organized and careful with your various parentheses and crap like that. There's a lot of negatives floating around.
Wait.
Alright, number 3, super great. Try to do it, and then a certain thing happens that's really sad. Well, no.
That's really sad.
Well, it's a little bit sad. Depending on your,
It's just hard to
philosophical
grasp.
positions on mathematics.
Okay, Mr. Anderson.
Alright, so
Looks like a little circle thing.
anyway, this is a half decent picture of the two curves. This parabola is x squared minus 1, and this curve is y equals 2 cosine x. Alright, now, following up from the previous problem we just did, what seems like the obvious thing to do right now, yeah, to find the points of intersection.
Oh, no.
Oh, yes. Or actually, no. Oh, no, I agree. What's wrong with finding the points of intersection between y equals x squared?
It's like hard to
You just like, it's like hard / like you can't, it's like impossible.
Make the calculator.
Right? Yeah, so, I mean, there's actually some interesting things going on here. You just notice that you've never been asked to solve equations like this before, because you kind of just can't. And you can't in the sense that there's no closed form expression for the solution to this equation. So you just have to do this with technology. So, yeah, get out your calculator if you have not already. And as I showed you how to do the other day, find the points of intersection between these curves.
You guys can show me calculators.
And then you have to do that thing. Was that just yesterday that we did this? Or 2 days ago?
It's like 1.26 negative 1.26. But you don't need.
Make sure your calculator is in radians.
Hey.
Yeah.
You need something?
Oh god.
What?
Top curve.
What's up?
Next. Can someone, Maya, grab the thing and go handheld
Oh, sure.
so you can see the TV.
should beat loud.
Oh, man.
Oh man,
Hi everybody, Maya here.
Okay, so we have
Yeah, thanks.
2 cosine x. I put into y1. X squared minus 1. I put into the y2. Duh. Okay, and then we could just choose a nice window, like, I don't know, -2 to 2 or something, and this should also be good. And when we graph these 2 curves, we should get a picture that was almost exactly like what was on our paper. Yeah, it is. And also this thing is odd, or even, so I'm going to pull the like even trick where I'm just like 2 times. So the only thing I care about is where these curves intersect. So you do that thing, right? Second calc, intersect, and then it asks which curves would you like to intersect? Yeah, that one. And then you just say, scoot that over a little bit towards that point of intersection, hit enter, and it's going to find that point of intersection. The intersection is 1.265, but we don't do any intermediate rounding, so the immediate thing we have to do after that, I talked this already, right? Quit out, type X on the home screen, there's my number, and you have to store it under a particular variable, like let's say A.
Wait, so what's the command to get the?
So it's actually 1.267. You lied to me.
Intersect.
Oh no.
This
Where do I go?
is, I'm going to write 1.265, but really I'm going to use the stored value in your calculator. You're back up here?
What? Yeah.
Yeah. Okay, so what am I going to do? I want to find the area of this green region. So I am going to draw my representative rectangle. What are the, that's kind of whatever. Alright, what's the height of this representative rectangle? Well, it's 2 cosine x minus x squared minus 1. So I want to take the rectangle whose height is 2 cosine x minus x squared minus 1, give it a little thickness, which is dx, and add up all those rectangles from, I'm going to go from 0 to 1.265 and then multiply by 2. Right? Because I doubled it. Everyone with me? So right. Okay, but I can't do that problem because I need to use that stored value 1.265. So that forces me to do the rest of this problem on a calculator. So we go over here and we do all that. So hopefully you did it already. We go math 9 and we're going to go, first of all I want twice the integral from 0 to the stored value a of, oh here comes another fancy move. If you go to y equals, you see it's just really cosine minus thing. So instead of having to retype annoying functions and possibly screwing up your parentheses, you can just type y2 minus y1, and with respect to x. And that, I believe, oh, something went wrong. Oh, because I should have done y1 minus y2. So that's annoying.
You just know you need to negate that.
Yeah, or I could just be fussy about it. What did I say? y1 minus y. It's like 5, but it's not 5. Assuming that we've done no intermediate rounding, the true answer is 4.995. And there we go. Everyone cool on that? Say yes and go to the next problem, which is interesting. I think my
Wait, why would we ever do anything by hand?
Maybe someday you'll become a professional curve sketcher.
But that's dumb because
pretty much am a professional
Really
curve
wanna
sketcher.
calculate.
Should not think about that.
you're professional.
I'm gonna get paid for this job, so I think I'm a professional.
At what point did you get
Your
this
math.
good at math?
Do about 7 times on calculus and started getting pretty good at it.
Wait, so the first few times you're pretty bad?
Do your math.
Is this right?
The most challenging part of these problems is not doing the calculus per se, it's in figuring out what the hell's going on. So it's really all about making a good picture, partitioning it correctly. No, you can't use your calculator. Or at least you don't need to, so you should.
Oh, I get it.
Yes,
So I'm sounding like a whore.
But the y component doesn't really matter because there's precision.
Y equals
Okay.
X.
Yeah, so, wait. Actually, yeah, you probably did it right. But before I let you guys just do your own
No, it
thing,
does matter.
let's talk about, there's like a cool way to do this. So, find the area in the first quadrant enclosed by the curves y equals x and y equals x squared over 4 and below the line y equals 1. What? Okay, so, time to make a picture.
So they both intersect with 0.
So first of all, there's like the line y equals 1, which looks like this. And then there's also this curve y equals x, which looks like this. And there's also the curve y equals x squared over 4. Okay, so first off, where does x squared over 4 intersect y equals x? Well, can I just do that from looking at it? Well, I'll just do it probably. So the answer is at x and 4, yeah? So that means, like, way off my paper, these two curves are gonna, this parabola is gonna intersect this curve. So where is this parabola at, say, well, when is this parabola equal to 1? That's also a question that I kinda wanna ask, right?
Well, you should do where 1 intersects both of them.
Yeah, each of them, right? Yeah, where does 1 intersect x squared over 4? Well, duh, that's gonna happen at 2 and negative 2. But I only care about the first quadrant. So here is my 1, here is my 2, and hopefully you guys all got a picture very much like the picture I got.
Yeah.
Yeah?
4, 5, 6.
But well, you Shushan, you have to shade your region. That's like important. So the region is, reading this again, the area in the first quadrant enclosed by the line, the parabola, and below the line y equals 1. So I got this. Okay, I'll let you guys get too much of a head start, so some of you are like done already. What makes this problem a little bit more interesting than previous problems? You can't just subtract. Can you articulate why you can't just subtract? Alex.
There's an extra bit of the line y equals x above like the line y equals 1. So like if you just subtract and you actually get like a bit above the line and that's even the line.
Okay, you're rambling a little bit. Can someone else say it differently?
You have
Yeah, Alice.
They don't like end at the same.
The what doesn't end at the same
The
time?
two curves, one goes to.
Yeah, it's hard to exactly say what's going on. The math teacher way of saying it is that there simply is no representative rectangle which I can partition the entire integral up into the sum of.
So just do
Would-
two separate.
Yeah, so that's one idea, right? One idea is just to say, look, I'm gonna have to go from 0 to 1. I'm gonna take a rectangle which is bounded on the bottom by the parabola and on the top by the line, and then I have to do a separate integral from 1 to 2, bounded on the top by 1 and on the bottom by the parabola. Does that make sense? Chris, you even did this already, right? And got an
Yeah,
answer.
but I think I see probably a better way.
Oh, is there a better way, Maya?
Sorry. You could just take the area between the y equals 1 for like 0 to 2 of 1, the integral of from 0 to 2.
Oh, and then
of 1
subtract out
minus-
this piece.
Yeah.
Yeah. That's a cool. That's a cool geometry thing. There's something even
Yeah.
cooler. Yeah, Sarkar. Question?
I think that's right.
Oh, yeah. I think so too. Okay. Even cooler. Who says we need to partition this interval into vertical rectangles? Why not
That is-
horizontal rectangles?
Because that sounds
Oh yeah.
How do you subtract
Oh
horizontally?
yeah. So expand your mind. Integration is not about finding the area under a curve. It's about adding up an infinite number of infinitely small things.
Wait, so this is thinking outside the box?
What do you want? Oh,
You're
you-
turning the box over.
Okay, so what we're going to do now is we are going to partition this integral up into a bunch of horizontal rectangles. And well, why is that better? Do you see the beauty of this?
So there's only one integral.
Because now there's only one integral, right? Because every single rectangle on that region, it can be composed, can be thought of as the difference between the x coordinates of these two functions. Okay, so whereas I could express this curve as y equals x squared over 4, what I really need to do now is partition the y-axis up into subintervals, and I want to choose an arbitrary y value between 0 and 1. And what I would like to know for that arbitrarily chosen y value is what the x coordinate is of each of the two curves, right? So you need to be able to take this parabola y equals x squared over 4 and express it as a x equals function.
Well,
So
can
it's
we
like
just
x.
use dy and the integral?
So x equals 4 root 4y.
X equals, yeah,
2 root y.
x equals just 2 root y. Yep. And then over here, since it's just y equals x, we're going to write it as x equals y. So what we've done now is come up with formulas which will take an arbitrary y value input and tell you what the x coordinate is. Therefore, it becomes possible to talk about the height of this rectangle. And what is the height of this rectangle in words? Yeah, it's the differences in the x coordinates of the two curves, for that particular y value. So it's just like he says, it's 2 root y minus y. And what is the width of each one? It's just like dy.
Okay.
And the fact that we're taking this integral sideways is really like irrelevant, right? Because all that matters is I'm taking a thing, a height of a rectangle, a width, and I'm adding them all up. And
Well, it might as well be the other way at that point.
what?
Because it's the same area
Oh, yeah.
whether it's the x or the y.
Are you saying just rewrite the variables? Is that something?
Yeah, you know what I mean? I mean, like,
Okay, so I'm taking the integral of 2 root y minus y times dy, and I want to integrate from what to what? 0 to 1 up the y-axis. Go. And see if you got the same thing. Have you done? Just taking a break.
Yeah.
0 to 1. Yeah, you're right.
0 to 1.
That seems like.
Yeah, you did.
Yeah.
So it's just 4 3 times 1.
Good. How we feeling about the sideways business? Good. Okay, what should we do now? Might as well just do the last problem. Go for it.
It looks real complicated.
Find the area enclosed. Is this possible to do without the horizontal one?
I think this is just a normal thing again.
Not exactly.
Not exactly.
On the bright side.
Okay, let's find out.
Intersect is 0, 0.
Is this factorable?
There we go. Hey. Move this out. No, I don't think so.
If you want to find where the roots of the third one are, you can find the intersects without it, but if you want to find the roots.
Oh yeah, but who cares about that?
Why do you need the roots?
Well, you know if they're.
Because if you want to make a pretty picture, basically. It's kind of hard to
Also,
understand.
you have to know if they're greater or if they're. Oh no, you don't.
No, you don't, because that's
You
pure
don't.
difference.
Never mind.
I don't know.
Yeah.
I don't know.
Don't say anything.
What's the good one?
I drew this wrong.
Oh, have you been here this whole time? Yeah, right. Just like over there.
What?
You know what?
Why?
Actually, I don't know if you do. I don't know.
I thought it was the name X.
You do need to
I just realized how cool
do
calculus
two
is.
intervals.
Yeah, it's pretty cool.
Because now I know
Or
where
can you use
the
absolute
vertices
values?
of the parabolas are. I never knew how to do that.
Yeah.
4, 6. It's also 2. This one is both. 0, 2, 2.
Kind of just like
Now it's stuck in my head. Probably.
Okay, so I have these curves intersecting at 0, 2, and -2. Agreed? And then that's like 3 or something. So maybe I should figure out what that is. 0 dot, at 2 we have 2. And then at -2 it's -8. Is that true? Fast has gone silence. No, -10. -10, right? So. And then what does this cube look like?
the house, like the area is not that